Welcome to Radio Board Podcast. We are 3A group. Today we are going to do a presentation of radioactivity. To begin, I'm going to give a short introduction about radioactivity. Radioactivity was discovered by the physicist H. Becquerel in 1996 because sees that some minerals emit energy on its own, energy that could pass through objects and leave marks. Radioactivity is the release of energy from the decay of the nuclei of certain kinds of atoms and isotopes. Atomic nuclei consists of protons and neutrons bound together in tiny bundles at the center of atoms. As a result, radioactivity substances are transformed into other elements. Now is Hector's turn.
Hello, I am Hector and I'm going to talk about types of radiation. There are two types of radiation. Alpha particles are helium nuclei formed by two protons and two neutrons. Beta particles are electrons, and the gamma rays is electromagnetic radiation, similar to like X-rays, but they much bear more energy. Radiation can be stopped. We need most protection from gamma rays because of their high energy and penetrating power. Now is Gonzalo turns.
Thank you, Clara and Hector. Now we're going to talk about the origin of natural and artificial radioactivity.
The discovery of radioactivity took place over several years ago, beginning with the discovery of X-rays in 1895 by Wilhelm Conrad Röntgen, and continuing with such people as Henry Becquerel and the Curie family.
Natural radioactivity is the most common, representing 70 to 80% of the total. It comes from uranium, potassium, thorium, or even space, like cosmic radiation. There are alpha, beta, and gamma particles, synthetic or artificial, come from bombarding isotopes with small atom particles, making possible particles that doesn't exist naturally.
The applications are radioactivity isotopes are presently used in many aspects of human life today. Most people recognize radioactivity's contributions to industry, research, and war.
What is half-life? At its core, half-life is a measure of time. Specifically, it's the time it takes for half of the atoms in a sample of a radioactive substance to decay. Think of this way: imagine you have 1,000 identical unstable atoms. They are all thickening, waiting to transform into a different, more stable atom by releasing radiation. If their half-life is 1 year, after that year about 5,000 will have decayed. After another year, half of the remaining 5,000, that's it. Another 250 will decay, leaving you with 250 of the original atoms. This process continues, reducing the quantity by half again and again. This is unpredictable, exponential decay, not a linear one. Decay takeaway half-life is constant. It doesn't matter whether you have a ton of material or just a speck. That log thicks at the same rate for that specific isotope.
Well, it's my turn and I'm going to talk about the decay curve. This brings us to the classic decay curve. If you were to graph the amount of material versus time, you will not get a straight line sloping downward. You will get a curve that starts by dropping steeply and then gradually levels off. That curve is the signature of half-life. Each point on that curve is exactly half of the previous point after a fixed time of interval. Scientists love this curve because it acts like a finger point. By measuring how much of the parent radioactivity element remains compared to the stable daughter element it turned into. We can trace backward along that curve to calculate the age of a sample. This is the heart of radiometric dating, and it's Fran turns.
I'm Fran, and I'm going to talk about nuclear fission. The first time this term was used was in 1939 by Otto Frisch and Lise Meitner. It's the division of heavy atomic nucleus, like uranium or plutonium, in two lighter nuclei of roughly equal mass, a process that releases a large amount of energy. Fission may occur spontaneously or be induced by the excitation of the nucleus with particles electromagnetic radiation. During fission, a large quantity of energy is released, radioactive products are formed and several neutrons are emitted. A heavy nucleus splits into lighter nuclei, releasing energy, radioactive products, and neutrons. The separate fragments repel each other due to their nuclear charges, gaining kinetic energy. As the nucleus adjusts from its deformed shape, the formation energy converts into internal excitation energy. This leads to the evaporation of neutrons and prompts gamma rays. For example, do you know the atomic bombs from Hiroshima and Nagasaki? I'm sure you do. These are the perfect samples of nuclear fission. Two of the bombs that wrote a page of our history, and now it's Claudia's turn.
Thanks, Fran. And now it's my turn to explain how the nuclear power plant works and all its steps, and it is very interesting process. For a start, heat is generated by fission of uranium in the nuclear reactors. Then control rocks are then introduced to slow down the clean reactor and thus control the release of heat. These steps is very important to prevent accidents like the one that happened in Chernobyl. After that, the released heat is transferred to the heat transfer fluid in the first circuit, and the heat from the fluid generates water vapor in the second circuit. The strain for the second circuit moves the turbine, which is turned the generator, which transforms mechanical energy into electricity, and so that this can be transported through the power lines. The electric voltage is modified using a transformer. With this, the vapor from the turbines is sent to a condenser where it's cooled down and turned back into water before returning to the circle, and so that the water used can be returned to the environment. It is the first call in a cooling tower. To finish, in my opinion, I think that nuclear energy is fundamental for today's society because it warrants a stable, constant electric supply with a greenhouse gas emission. And with this, the operation process of a nuclear power plant comes to an end. Thanks for your listening, and I'll leave you with Claudia.
Hello, my name is Claudia, and I will explain what nuclear fusion is, its advantages and difficulties, as well as the analogy and astronomy and the possibilities. Nuclear fusion is a nuclear process where two atoms are forced by their environment to combine and release massive amounts of energy. Also, it is the reverse of nuclear fission. Why is nuclear fusion so important? Because it includes reducing reliance of fossil fuels for electricity generation, producing emission-free electricity during operation, being inherently safer than nuclear fission, generating minimal nuclear waste, and providing a baseload power. But there are some difficulties include technical challenge, high cost, and uncertainty around regulations. Also, nuclear fusion is possibly and actively begun developed, with significant global investment. Kept in mind that also what happened in stars is analogous to nuclear fusion in astronomy. It is also important to know if nuclear fusion is seen as one of the most sustainable and promising energy sources of the future, offering clean, safe, and almost inexhaustive energy, with no carbon emission or low-lasting waste. And finally, in my opinion, nuclear fusion is important because society positions it as a revolutionary and sustainable solution to the current energy and climate crisis. Thank you for listening to me. Bye.
The region of radioactive waste is waste containing radioactive chemical element that has no practical purpose. It is frequently a byproduct of a nuclear process such as a nuclear fission. Waste can also be generated during the full process for nuclear reactors or weapons, or in medical applications such as radiotherapy or nuclear medicine gestion. For over 13 years, they have developed solutions and expertise for the perfection of radioactive liquids, the solidification of waste, and development of strategies for its management. Problematic. The biggest problem with it is high hazard level, the number of years it has been active, and the complexity of its storage. It also presents significant health risk, one of which is cancer.
Hello, I'm Valeria, and to start with, I'm going to talk about the use of radioactivity in nuclear medicine and radiotherapy. Radioactivity in medicine is mainly used to diagnose and treat diseases, particularly in oncology, cardiology, and neurology. Nuclear medicine uses injected radiopharmaceuticals to obtain image or destroy tissue, just like we obtain a diagnosis that uses radioisotopes to detect cancer cells. Techniques include positron emission tomography to detect cancer, heart, bone, or brain DNAs, and therapy that administers radioactive substance that specifically target tumors cells to destroy them. Use it in thyroid cancer, neuroendocrine tumors, and bone metastases. Radiotherapy. There are two types of radiation therapy. External radiation therapy. Linear accelerators emit high-energy radiation beams direct at the tumor, destroying the DNA of cancer cells. And internal radiation therapy. Cell radioactive sources are placed inside or near the tumor, implants, allowing high localized, thus with less damage, to healthy tissue. Now, I'm going to talk to you about reflection in radioactivity in nuclear medicine, and radiotherapy are extremely important today, enabling accurate diagnosis and life-saving cancer treatments. Their sustainability depends on radiation protection, personalized thus to reduce side effects, and the management of radioactivity ways to ensure long-term safety. Now I finish with the use of radioactivity. I leave you with Pilar. Bye.
Thank you, Valeria. Now it's my turn. I'm going to explain another example of food preservation. Pay attention. Food preservation includes processes that make food more resistant to microorganism growth and slow the oxidation of fats. Food preservation may also include processes that inhibit visual deterioration. For example, defreezing vegetables. Freezing is a simple, easy, and convenient way to preserve vegetables. The process takes little time, but the cost of a freezer at the utility cost make it one of the more expensive ways to preserve. The freezing process preserves nutrients and provides a fresher flavor than canning of drying foods. I finished my part, now it's Mario's turn.
As Pilar said, I'm Mario and I'm going to talk about the last part of the podcast, the third example of the uses of radioactivity. Since the discovery of nuclear energy, it has had numerous uses, some of which are the electricity production and environmental protection. So, in my part, we are going to talk about one of them, the use of radioactivity for the restoration of artistic and historical heritage. To begin with, the AAA is an agency that supports experts from all over the world and oversees the process. In addition, scientists use various radioactive techniques to keep our heritage safe and to learn more about it. One of the big ones is carbon-14 dating. During its life, every living thing takes a tiny bit of radioactivity carbon, As is the case, the carbon slowly goes away, and as a result, scientists can figure out how old is something is by measuring what's left on certain elements. You know, the shard of Turin is a famous case where carbon-14 was used to figure out how old was it. Furthermore, radioactivity is also used to protect and clean historical objects. Museums actually use gamma radiation to clean up books, textiles, and wooden items. This product removes fungi, bacteria, and insects. Finally, X-rays and neutrons give experts chance to examine inside artworks before they start the restoration process. This way, they can uncover any hidden damage without putting the piece at risk. This has been the podcast, so I hope you like it, and we see you later.